Okay, so let us start today's journey. Okay, so today we are going to learn the physics of Spiderman's acrobats and the physics why to smooth sticky surfaces stick to each other. And just a moment. Yeah. Uh, so we are going to learn today physics of Spider-Man's acrobats, and which you might have seen in movies and must be wondering what's going on, whether it is real or fake. Of course, it is fake, but whether we can pick up some ideas from uh, this physics of that and chemistry of that, can we design some engineering products out of these uh, lectures which we are uh, undergoing? And another point is the physics of smooth sticky surfaces. You might have wondered in the kitchen or some other places, two very smooth surfaces, they stick to each other, and no matter you try a lot, and they remain sticky. But we are science students, so we can't just say that two smooth surfaces. There is nothing. It's not a scientific word, right? Smooth is not a scientific term. Stickiness is not a scientific term. We have to, when we say stickiness, we have to give some numbers, right? As a scientist, we are supposed to give some numbers. What does it mean? Can we numerically, can we quantify the stickiness? Can we quantify the smoothness? And how sticky is the sticky? How smooth is the smooth? Right. So these questions are not easy to answer if you go into detail. And third example would be lizards climbing on vertical walls, not just the vertical walls, but upside down. Can you do that? Can you climb on vertical walls, or can you might have seen in your house the lizards hanging from the ceiling, right? And sometimes you wonder they will fall off on me, and they usually do not fall, and they sleep there, and they do all kinds of things, running around, and sometimes they do potty on you, right? And when you are studying, it will drop like put on you somewhere, right? Um, so they do all kinds of like catching mosquitoes, and it's a fear for people, lizards running around here and there. So nature has used these physics of forces in such a bright manner, and so this gives idea. This is called biomimetic engineering. Actually, once you understand these surfaces, interfaces, then you can design some new products without harming the nature, right? When you are in the nature, when you learn ideas from nature, of course it's not that easy to mimic the nature, because for example, if you want to mimic the brain, so brain consumes almost 10 watts of the electricity, and you know the 10 watt of led bulb, that is sufficient for a small room. But 10 watts, same 10 watt of energy is being used by such a powerful brain. And you take example of computer CPU, central processing unit. It consumes a hell lot of power, but it's nowhere comparison to the brain power, right? The memory and everything and computational powers. Of course, supercomputers are beating some of the analytical skills, artificial intelligence, but there is again a lot of power consumption there, and then all functions are like emotions are missing. Not all the functions are mimicked by artificial intelligence. A very small part of human brain can be mimicked by artificial intelligence. And that's the next research, that whether we can transfer the personality of a person after the death into a computer. For example, my personality can be tabbed from my brain uh, to a computer. Of course, it could be done. It doesn't defy any laws of physics. but that doesn't constant, that will stop evolving, that will be frozen me at the time of my death, when my uh, uh, like brain brain imaging was transferred to a machine. So I, as a human, constantly evolve. Uh, all the time. I mean, I'm not the same. Every moment I'm changing, my memory is changing, my body is changing, right? But when scientists transfer, for example, my brain image to a machine, so that will be the brain image of that uh, time. So there are many problems actually in the life is not simple. And another example will be the talcum powder falling in lumps. We know the example of salt, table salt. It falls freely. But if you look at the talcum powder, it falls in lumps. It doesn't fall freely, right? The lump will come on your body, and then you have to rub it and spread it all over the body. I personally don't use talcum powder. I do not like, but in childhood, probably in hot summer in Rajasthan, where I was born and grew up, my mother will sprinkle some talcum powder on my body when there will be some heat related issues on the skin, right? I think people in Rajasthan, they know. So it is quite itchy sensation on the skin. And for kids, it's a really uncomfortable situation. So sometimes mother, they will put the mint with, with some mint smell, something. So, okay. Some people put sandal paste, that also helps. So we covered a lot much about forces last time, and we learned about van der Waals forces. We learned about Lennard-Jones potential. We learned about attractive and repulsive potentials, and then we calculated the force. But it was all for two molecules, right? It was not for the collection of molecules. So what do we do if we have macroscopic bodies like AFM tip or salt grain or talcum powder grain or basically lizards' feet, or Mr. Spiderman, okay, jumping around with the on or climbing somewhere or in the British, in the London, buildings. Okay, can you do that? So these things cannot be solved by simple formula which was given by this London and Debye London and okay, third one, London force, Debye force, and another one, third one. Anyway, so because it was given for two atoms or two molecules. So the Hamaker was able to solve this picture. So as I mentioned that he used pairwise summation, and he did some approximations, and this is his paper where he calculated London dispersion formula, and then he basically did volume integral, which was valid only for surfaces with no porosity, with a continuous continuity in the medium. But anyway, whatever he did, but we have a workable equation, and we discussed about this equation last time, and basically U is the potential energy, van der Waals interaction energy, which is a function of R1 and R2, the radius of two spheres, spherical objects, for which he originally gave the equations, and they are spaced apart by distance z. And if we take R1 and R2, if we, in actual life, this is basically the distance. This is R1, R2, and anyway you can take it as R or D, whatever. So if the distance between spheres is too small, which is the case for two sticky surfaces like flat plates which get glued to each other. That means R is very small. That's why they stick to each other. Then we will see that how van der Waals forces at a smaller distances can be so powerful that these surfaces get glued without any glue. It's a basically glueless glue. So, or you can say that sticky surfaces, adhesive, self-adhesive surfaces. So this has got a lot of applications in the in the daily life. For example, you would like to put a doormat, which with these kind of surfaces made of some plastic materials. So if somebody walks with dirty shoes, so these adhesive surface, self-adhesive surfaces will collect all the dirt from the shoes, and then you can wash it off, and they are reusable because they are based on the van der Waals interaction. There is no actual chemical glue there; it's all physics. So, especially another point will be, for example, gloves of these kind of surfaces. Can you make some kind of gloves for army? So, and also like socks or something, some body suit which will help soldiers to climb difficult surfaces like Spiderman. Can you make our soldiers Spiderman, so that they will, when they are in difficult situations, they will be able to. It will help them to climb difficult. It won't definitely. They won't become Spiderman, but at least to some extent, their effort, bodily effort with heavy arms and ammunition, which is usually there on their shoulders. All of you are aware of that. They carry a huge amount of load on their shoulders. So they can carry different substrates, surfaces like lizard. So there are a lot of ideas I mean, people are carrying around. So finally, as I mentioned that we can calculate the potential energy, which is minus sign is for attractive force, basically attractive, this positive energy. A is a Hamaker constant, R1 and R2. Obviously, they are the radii of two surfaces, two spherical objects. R is a surface to surface distance, not from center to center this time. So it's good. So we can now we have the formula, so we can now start calculating. We can get some numbers for the problems we discussed. So okay, so here we can, as I mentioned last time, that if you take a derivative over the interaction energy, you can get the force. And one more thing, that the enemy is KBT, thermal activation energy. So basically, this potential energy has to be greater than the this KBT. Otherwise, temperature is also enemy. All the atoms and molecules, they are constantly at motion. So they won't keep the things stable for you. So most people underestimate the strength of van der Waals forces between bodies in a vacuum or air so far. What is the reason that van der Waals interaction, they are so weak, but they can dominate for smaller particles? The science of free-flowing salt or sand and fine floor falling in lumps, जो घर का आटा होता है, that also falls into lumps. Maida, if you compare at home between these refined wheat flour, what we call maida, right, and the whole wheat flour, which is ground in these mills actually, right, which is usually coarse. In Maharashtra, they eat quite finer flour, but in Rajasthan, usually north, I remember Rajasthan and Punjab and other Uttar Pradesh, they usually eat coarse wheat flour. So if you compare whole wheat flour and refined wheat flour, you will find that maida really falls into lumps. You can do this experiment. And if you take suji, which is called, I think, semolina or whatever, so that falls. Let me close the doors because AC. So at home, I think all of you are at home, so you can compare third object. You can take that Suji, and that is even much free flow objects. You can see each individual grain. It never falls unless it is wet, right? Uh, it will it will fall freely, right? So if you you start from talcum powder, which is very fine. When you say very fine, what do you mean actually? So can you calculate if you have the grain size of these 3-4 objects which I mentioned? Let us do some mathematics, very simple mathematics. So these are the examples which will excite you. Mr. Spider-Man, can you make our soldiers like that? Otherwise, it just remains a movie. Okay. And for example, spider silk thread is considered as one of the toughest object. Again, it's force, the area of force, which should be studied here, because spiders can just shoot the protein. It's just some kind of spider silk protein. We all know actually. So which is quite, which has got. I mean, nobody since size. I mean, spider didn't go into chemistry lab and do the synthesis of that protein, and there was no proteomics done. So nature does simple things with a lot of interesting magical output. So we just so people say that best scientist is the scientists which observe nature and remain in awe. Oh wow, what a wonder! Remain like not in like why to wow, not like in worry or anxiety or stress. We should be in awe, okay, and study the science behind that rather than going into the mystical thing that, oh, God created like this. Okay, God created fine, but can we do something interesting with the okay, without exploiting the nature? Obviously, this picture, if you see it, it's taken by me. This one from in National Chemical Laboratory, the colony area, beautiful lizard. If you see this gecko lizard. So basically, there are two parameters. If you see, if you reduce the R, so this force, van der Waals force, is going to be. We still call it van der Waals force, even though it is not the original van der Waals force. You can see this is now R is square here. Okay, because now it is Hamaker's contribution has come in, so it's not like 1 over R to the power 7, not 6, 7, right? We took derivative, so one more R. So A is the Hamaker constant and R1, R2. So if you see that if I increase R1 and R2, so this is going to increase, right? But R distance, so basically that means if I take smaller particles, van der Waals force should become weaker. Yes, it does, but R is also smaller. Small R is also that also becomes smaller. And please don't underestimate the reduction in the strength of inertial forces such as gravity, drag, lift. That decreases to much greater extent. So there are two forces acting in opposite direction. Van der Waals force would like to form like lumps, and gravity would like things to fall apart. It should be pulled down towards the earth, right? So it turns out that if you take smaller and smaller objects and they fall into lumps, and van der Waals force is so that's the reason you have aggregation of smaller particles when you make colloidal. So this is all colloidal chemistry, colloidal physics. This is all colloidal, part of colloidal, hardcore colloidal chemistry. What I'm teaching is actually hardcore colloidal chemistry. So if you see that, so free flow occurs with particles greater than 250 micron, which is quite large. So you can start seeing that lump kind of formation when the particle size is smaller than 250. So we are here discussing about dry powders, finely grained. So we are not discussing about capillary forces yet. In the next lecture on Monday, we are going to discuss capillary forces. Then you will be surprised that how water can rise in such a tall trees, normally you need very powerful motors in your house to lift some amount of water to the overhead tanks, and that requires huge amount of energy, and your electricity bill goes up. But you can see millions and millions of trees, and very tall trees, and lot of water. If you squeeze some leaves from the top of the tree, the whatever you call it, okay, in the top foliage. So you can see that if you squeeze them, you can see water coming out. So, and there are so many leaves actually. So lot of water is there at certain time. It's not just the capillary forces. There are many other things which we'll discuss, which are responsible that you are not consuming that much of energy. Which is, so what I mean to say that nature is very energy efficient. Same amount of water, if you have to ask any engineer to lift, so they will take a lot of energy. Same example I gave about our brain, comparison of brain and computers. So, so then our objective is finally AFM. So we keep coming back to the atomic force macroscopy. When we learn some lesson, we come back to that AFM, we apply that, and then we go to the next problem. So they will keep doing that actually. So now we have some interesting equations. So we can, suppose you are working, so this is basically apex of AFM tip. So this flat area is called cantilever. This is all made of silicon nitride or silicon coated with silicon oxide. Sometimes the backside is coated with aluminum or gold for certain purposes we'll discuss later on. So you can see this is colloidal bead which interacts with the surfaces. So so this is basically spherical tip. You can easily calculate. So one side is flat, which is your sample, and another side is sphere. So you can calculate the force between. You can see one example here. So one side, your sample is flat, and the probe is spherical. In this case, particular case, so with Hamaker's help, we can easily calculate the force, van der Waals force between two objects if we have the dimensions right. In case we have a pyramidal tip, not the spherical tip, so then we can use this formula easily, right? If we have a conical tip like this, okay, instead of pyramid, we have a cone like birthday cap. Okay, birthday cap can be also pyramidal these days. Okay, so you can use this formula. So this Hamaker is quite diverse. You will realize very soon. I'll give you an entire table where you can pick up any surfaces and you can easily calculate. As I promised that we'll do some calculation. So here, for the sake of simplicity, we are going to put Hamaker constant in terms of energy joule, and we'll put 10 to the power minus 19 joule as a typical value, which is actual. Okay, so if we take two macroscopic bodies, so we can calculate. For example, let's start with two macroscopic spheres, pretty large spheres, 1 centimeter radius. So diameter becomes 2 centimeter, which is quite large actually. You can see these are like marbles, which we use. I think slightly bigger than marble. 2 centimeter will be somewhere here. So I'm sure you might have played with marbles as a kid in villages. So similar to that, if you take two glass marbles, so then, and they are contact with each other, and if you bring them close to each other at around 2 angstrom, okay, and this marble should be smooth, not like, we'll discuss about that. Surface does matter when, and I promise you that I'll explain you. Okay, let me explain you what is smoothness and what is roughness. That has to be clear. So if somebody asks you smoothness or roughness, you should ask some people use this term optically smooth or atomically smooth, because many times you can't, these are scientific terms. When you say optically smooth, it's highly scientific term. Just if you say this surface is smooth, it's not a scientific term. Why optical smooth term is scientific. When this roughness is less than the wavelength of the light, then you can say that optically smooth. And you can do a very simple experiment to check whether it is, you don't need any hi-fi instrument to check whether the surface is optically smooth or optically rough. Just do simple thing. You take any ruby red laser, which is available in all these pointers, laser pointers, similar to that, and you shine that laser to that surface. For example, you shine that laser pointer to the wall of your apartment or your house, wherever you live, and if suppose there are 10 people living in that room, your mother is there, your father, sister, brother, or anybody, they can all see that spot of red red laser, at the wall. They can see, they can all see. You can see that spot. So that means the light is reaching to your eyes. Your father, who might be sitting in a corner reading newspaper, in another corner, he can also see that light. Okay, that means light is getting scattered and reaching to everybody's eyes. How it is possible that you're shining certain light laser at certain angle, but it is reaching to everybody's light? That means surface is optically rough. So it is like zigzag, zigzag. You can, if you zoom that surface, you can. I don't have blackboard, so I cannot draw it. And this Zoom whiteboard is quite inconvenient, so I never use it. And to enhance my capacity, I was planning to buy a new device, or there is a laptop which has like Lenovo Yoga or something, which you can scribble on the screen, but it is maybe another time. I didn't plan for. I have that kind of laptop, but it's too complicated. Okay, that software is missing, but because I had to format that, and that computer is horribly slow, I'm used to Mac machines rather than Windows. So I don't want to go to that machine. So anyway, coming back to that. So if you shine the same laser light to, for example, your mobile phone screen, and you'll be surprised that this dot will disappear. Your father sitting in another corner, your mother sitting in another corner will not be able to see. So who will be able to see? Only another person who is sitting at exactly at the same angle, theta, basically perpendicular to the plane of that mobile screen. Okay, so it will get reflected exactly at that angle. You can do the same experiment on like shiny silicon wafer. You might have seen silicon wafer. So any smooth surface, the dot will disappear. So it's magic. In one case, the dot was seen by everybody in the house, and in another case, the dot was seen only by another person who is sitting exactly at certain angle. So that means that surface is optically smooth. You got it. Now, when you change the red laser to another wavelength, so that surface smoothness has to match. You don't think that this magic will work for like 1000 nanometer wavelength or 250 nanometer. So basically, that surface smoothness has to. Usually, these surfaces like silicon wafer, which comes from Silicon Fab Lab. I have checked using AFM long back. Okay, I wanted to check this, that smoothness is better than 2-3 nanometer. So you can see that it is definitely optically smooth. Now next thing comes atomically smooth. Atomically smooth, you can understand better, because that means there is one continuous atomic plane, and it's not like zigzag zigzag. So it's like for example, graphene is atomically smooth surface. Okay, so how can you check it? Using STM, scanning tunneling microscope, you can easily check. Using AFM also, you can check whether it is something is atomically smooth. So these are two scientific terms. So you have to be very careful when you use, and such many times people use unscientific terms in the manuscripts. Oh, this looks very nice. What is nice? Nice is not a scientific term. Okay, so using language in day-to-day life is a different thing, but writing something on paper is a very different thing. So always make sure that you use proper terminology. So coming back to our equation, you might have read, I gave you sufficient time to read. So you can see that this force is still not very small. It's quite millinewton or 0.2 times G, but it is still pretty much small actually, okay? But if we reduce this marble size to 20 nanometer, radius 10 nanometer, then of course this force will fall by factor of 2,500 to about 10 to power minus 6 Newton. So sorry, it has to be larger actually. It has larger the better, because we are talking about van der Waals attractive force, not the repulsive force. We'll talk about repulsive force also, electrostatic repulsive force, when we look at the charge object, because day-to-day life objects are not neutral. We are talking about neutral bodies, not about charged bodies. And that also brings a lot of complications, because the silicon surfaces, this surface which I'm talking about, they are not necessarily charged. Of course, metal is largely neutral. Okay, if you take two steel plates, but if you take two glass plates, they may not be neutral. There may be some trapped charges, some dipoles may be there. Okay, polarization may be there, local polarization, not like large scale polarization. It's not possible because it's a directed. We'll discuss about that. But we have to also factor in, because our enemy here is gravitational force. Okay, we are okay, so which force is at your side? Okay, so that you can easily calculate. And another thing that you can calculate is basically kBt. So finally, you can realize that even for the particle size 20 nanometer, this adhesive energy is quite large. And we can still, similarly, we can calculate forces for two planar surfaces which are in contact with each other at 2 angstrom. So planar surfaces can be held close to each other when they are ultra smooth. I mean, you got my point actually, which are at least optically smooth to each other. For example, if you take two silicon substrates and shiny side, if you put held next to each other, you can't, they will really get stick to each other. There's no glue. So adhesive van der Waals forces will be so strong that you can't, okay, so remove them. So you can read about that. The first reason I already discussed. Second reason is basically, as I mentioned, that there can be moment. We have been discussing that when you rub two surfaces with each other, there is always charge transfer, and one side becomes positive, another side becomes negative. Even initially, those surfaces were neutral. So that also helps to develop electrostatic attraction between these two planar surfaces, and it helps them to. This is a common problem in industry, very common problem in metallurgy. If you Google this topic, you'll find that industry, it's really common actually, that two surfaces that glue to each other, and it's very difficult to. Some people put a drop of liquid between two surfaces and then uh, to basically unglue them. And third point, obviously, it is a common sense that because these surfaces are so smooth that air basically is sucked out, outside air pressure also helps. Outside air pressure, which is atmospheric pressure, it also helps them to stay wherever they are. So so this is a combination of these three forces: electrostatic forces, van der Waals forces, and atmospheric air pressure actually. Another thing which we'll discuss later in detail, that real surfaces are not smooth as we have been discussing. So is it interlocking? I mean, there were a lot of experiments done that suppose these two surfaces are, this is zigzag, like, this two egg crates, hexagonally ordered, right? So there was a lot of experiments whether it is if you put two egg crates over each other, they get jammed actually, right? They get interlocked. So there was a lot of basically discussion on this topic. I'll discuss about this in the next lecture on Monday probably, and very interesting things in real life applications when you design this. Surfaces which do not they do stick to each other, or they do not stick to each other. For example, sometimes you want surfaces which should not stick to each other, right? I mean, depending upon the application. So if you do not know the right science, you cannot design this. For example, polymer surfaces. I think there are some polymer chemists also. I'm sure Rajendra is a polymer chemist. So for example, Rajendra wants to design some polymers, uh, which, uh, which basically doesn't, in one case, you don't want them to glue to each other. So how do you do that? So as I promised that this table give you direct access. Any question?
Yes, sir.
Yes, yes. Oh, you are there. Any question?
Actually, I have one question.
Yes, yes.
How is friction producing heat, sir? So is it related to this what you're teaching? How can you
Yeah,
calculate the heat?
friction. Why does friction produces heat? See, in friction, you are applying some external kinetic energy. And in friction, what exactly happens that you are using that energy, and friction happens when the surfaces are porous, they are not smooth. So they might be interlocked. So basically, you are using that energy in moving one surface against another, like a shear force actually. So then a lot of energy get transferred to the surfaces in terms of heat energy. So that results into there is a lot of loss in the loss of energy. I mean, in the real life, the efficiency of these processes is not that much. So there is always a friction causes a lot of transfer of energy to the. Now you can ask me the question that what is the science of heat? I mean, why when I say this temperature is higher and this body temperature is lower, what does it mean? So basically, higher temperature, heat is nothing but motion of atoms and molecules. So heat, there's no in physics, hardcore physics, we don't consider heat the way the normal people consider the heat. Heat is nothing but the movement of atoms, the vibration, actually vibrational energy, basically the heat. So more the suppose some body is held at high temperature. So of course you can read using some thermometers, using IR thermometers. So, but in physics terms, that means atoms are moving at much greater speed, actually. And finally, it leads to basically vaporization when these then friction is basically because of non-uniform surfaces. And yes, okay. Yeah. Any other question? Keep it informal. Please ask questions. I love questions. So. I'm sorry, last time. Rijwana, can you unmute yourself? I have something interesting to share.
Yes, sir.
Rijwana, you must be wondering that how in your PhD thesis, how could I ask so many deep questions? Because I'm not an expert of. Where is Rizwana? She disappeared.
Yes, sir. I'm here, sir.
Okay.
Yes, sir.
So, so I actually taught this course long back. I'll be teaching because there is a demand. I'll be teaching spectroscopic ellipsometry. That is the physics or chemistry which I will be teaching is that exactly falls into your area of expertise. It will help you tremendously. So I'll keep you informed because there is a lot of demand from students to offer that course as just like a discussion. It's not like a formal. You don't need to worry about formal examination or something, and you can be just relaxed and listen to me. It will help you to understand those boundary conditions and those things I was asking. You understand? Those evanescent waves and all those questions, and you will become like a dada of optics. Okay, Rijwana, you will become like really your basics, like John's matrix. You might have read about those things. Depolarization, how to calculate depolarization, amount of depolarization. So I'll make you an expert. Okay, if you you have to take pain of sticking to these lectures, and it will benefit you a lot.
I will, sir. I will, sir, definitely. And
You're ready, right?
yes, sir. And this class is also very informative to me because I learned the things which I didn't actually think about. I didn't think what kind of roughness and what kind of smoothness we are talking about, and there is optical roughness and such
Yes.
terms I never think about before.
Exactly, exactly. So it is very important for our students that they should know that there is something called optic. In that lecture, Rijwana, I'll be speaking in much detail about roughness. Believe me, this here I cannot uh, include those things. And yes, in this AFM series, I'll be telling you about different types of roughnesses later when we will do some data analysis of AFM images. See, that is just a bahana excuse. This AFM is, I told you in the beginning that AFM is an excuse for me to teach you so many interesting things actually. Now you realize, right? So
Sir, yes, sir.
this is AFM. This is not. This is less about AFM, but more about so many interesting things about you around the nature and okay, yeah, yeah. So I'm sure you will have fun. So okay, so
Yes, sir.
let me
Thank you
move.
so much.
Yeah. Uh, so this so now you can see that in real life yes.
Sir, I didn't get you get a clear picture on this friction. What I understand is that we are giving a force in opposite direction to the repulsive force, its body force on the van der Waals. So, because of the interaction of the two forces, is it possible to heat it emanated?
I'll be
So,
teaching
I'm
frictional
not
force,
clear.
Rajendra. I'll be teaching frictional
Yes,
force
sir.
microscopy. So you can measure the
Okay.
frictional energy, frictional forces. You can. So I'll be teaching in detail. I now I remember that I'm teaching that actually. It's part of the course. Frictional force is part of this. So I'll teach you there. So I'll tell you how to
Okay.
quantitatively how. For example, Rajendra want to know which surface has got more friction. Suppose you want to quantify two surfaces frictional energy. So AFM with AFM you can quantify, and it is one of the greatest power of AFM. I'll teach you in detail. Don't worry. I just now I forget actually so much of this course is very rich actually, very rich. That will answer this question. Okay, just hold on for 1 week actually, just 1 week. So you can see now there are two rods next to each other, parallel cylinders. Here you have a sphere and a parallel surfaces, two spheres, and in your laboratory experience experiments, you can come across variety of surfaces. So some of the simpler structures are given there, so you can steal the formula from here for the force and energy, and you can use it for your advantages. Here again, some more similar forces are given, and this I find very interesting. And if you see the reference has changed here, and believe me, this but at all this is basically a review article in Surface Science Report 2005. I tell you, my personal experience is that from personal experience that I learned a lot from this paper one single paper. It is about AFM, but it really opened my eyes. It teaches so much about surface chemistry. So much of surface chemistry is there about biology, surface biology. So application is, I wanted to read this paper just for AFM, but what I learned was, so much of so many you can see that this is 152 page. I'll be teaching this paper in bits and pieces throughout this lecture, so even if you don't want to read this, you are already reading that this paper actually, and but you can download it and dump it in some folder. I advise you to do that. So this, for example, this table is taken from this paper, and you can see this is such a rich table. I mean, you can find that this is real life. You have two materials. For example, you have two titanium spheres. For engineers also, it is so important. For example, you have a gold tip and gold surface. You may have silver, colloidal silver nanoparticle. You may have you can silicon nanoparticle, and medium two is air, and all kinds of things. For example, Rizwana's thesis, she was using zinc oxide. So you can approximate zinc oxide with this. Zinc oxide is not here, but you can approximate this with silica or some other material, or you can calculate also for like two Teflon materials. For Rajendra, this may be interesting. Like, how do you calculate the force or Hamaker constant between two Teflon material? And this is bovine serum albumin, BSA, the protein molecule basically. So you can see this is calculated Hamaker constant. Unit is joule again, and this is experimental, and they're quite close to each other. You can see that they're quite close to each other. And so these, another thing I would like to mention that these experimental values were calculated by using atomic force microscopy. So you can see that atomic force microscopy can give you values so close to the calculated values. So this is highly, that's why industries love this instrument, atomic force microscope, because it's quantitative, highly quantitative actually. So now we upgrade ourselves that if we have colloidal surfaces, how do we take care of that? Sorry, charged surfaces. And now we are going inside the electrochemistry. I'll not go too much deeper because many people may know this. I think many of my students are electrochemists. For example, I think let me see, Faiz is, I think, electrochemist. Darren is definitely electrochemist, but I'm not sure about others. There are many students. Sapna is a chemist, right? Sapna, you might have, Sapna is actually a professor of chemistry. Now she's settled in Pune. And I'm sure you might have read about electrochemistry. In electrochemistry, you read about DLVO theory. And you know that I'm a notorious person to go deeper. I want to read about DLVO, then I will come to their theory. So let us understand about the life of the scientist, because it will be injustice we just jump to okay. Yes.
Yes, sir, sure. Actually, I'm learning so more things from your lectures which I have never read in my life. So it's really interesting.
But this is chemistry, no? Electrochemistry.
Yes.
Theory and
Yes.
Double layer formation, right? When you take
yes. Actually, we jumped the things which we didn't get interested. So there are many things which I didn't read in my life, but by getting your lecture, it's really interesting. I'm feeling that I should read this.
See, Sapna, that also gives me energy. You might be thinking that, see, I had a lot of, I tell you something, my students, they know that 2 days I was having a lot of anxiety because this last lecture, link was completely wrong. The link,
Yes. I was not able to attend your Manipal's lecture. I tried my best.
Oh, I struggled with 3 laptops with the wrong link for 1 hour, and I was sweating badly, and students were also not there, and nobody. And then one of my, I called one scientist. She works in my group, and her kid was having one class on the laptop. She came with her laptop. She tried. She gave up. She was also sweating badly, and then we called them, and then it was very exhausting. And
yes. Even I downloaded the app too, but that is not working.
So that entire thing, and I worked very hard for that lecture. I was like, for almost for 1.5 days, I was working because I knew that it has to be really something very appealing. Anyway, so that yesterday was a little bit rest day for me, and little bit introspection and reading and this that. So these charges are can be cations. Basically, cation and anions can be monovalent, divalent, and trivalent, and we will see that which one is more. So we are now discussing about two competing forces. So electrostatic forces in some these you can take electrochemical cells. So let us understand formation of river delta. So river delta, some of you are Bengali like Debye. If you go to Sundarbans or anywhere wherever sweet water, river water mixes with the salty water, you can see that there is a tremendous amount of dust settles down there, and it is quite precious. A lot of things that it happens, like you know this fish, Bengali fish, what you call it, hilsa fish actually is, it breeds in at this merger of sweet and salty water. In fact, if you go to Alaska, this another nutritious fish, salmon. Also, salmon is actually Indian version of this hilsa fish. So what exactly happens that this river stream, when it comes from upper Himalaya, I don't know whether you have been to this upper Himalaya. I have been to those terrains where our Indian forces are currently fighting Chinese. 14,500. I have been to the highest petrol pump in the world. I have been there. Highest village in the world. I have been there. It is even higher than this Leh Ladakh actually. And it's so terrible. Even if you walk 2 steps without any luggage on your shoulder, one can just start huffing and puffing, and then air density is so low, so it is a miserable life. So when these glacial rivers starts from there, so a lot of these grains get, because of this soil erosion, so this water carries a lot of soil with them from upper Himalaya, and then it goes to the plains and through these large rivers like Ganga and Yamuna and all these rivers, Brahmaputra. And finally, but these particles, when they come from Himalaya, they go down, they start cutting down into smaller sizes. And finally, they are in the macron sizes actually. And depending upon type of minerals, which that's why these grains are different in sizes, colors, their chemical composition, but all of them are normally negatively charged. So when these negatively charged particles, they come into contact with this salty water, and you have a lot of these sodium ions. So immediately there is a charge neutralization happens, and van der Waals forces kick in, right? So electrostatic, earlier they were in suspension because of the electrostatic repulsion. Now this because of double layer formation, because this so this electrostatic repulsion falls off, and you have strong van der Waals interaction, and then there is this these clumps actually, and they fall off when So that's the reason that immediately that dust or settles actually, and then you have a lot of these river delta formation, which is a natural process. So I have written it up here that DLVO, these 4 scientists together, so this is called basically electrostatic double layer formation. So you know that it arises because of surface charges. For example, if you take, you can read all these things. So for example, if you take a charged surface and you put some electrolyte, in this case, we are taking salt water as electrolyte, considering that the charged surface, what will happen that these counter ions will start getting electrostatically attracted toward this surface, and there will be higher density. So we call it actually Helmholtz layer or Stern layer, but I think both are same. And finally, this layer, this concentration will fall off exponentially. As you go away from the surface, this concentration of these counter ions will fall off. And so this is basically given by Debye screening length. This is known as Debye screening length, lambda d, which is understood as the thickness of the diffuse electrostatic double layer formed by counter ions actually. So this is very interesting actually. This is highly applicable this depends upon the concentration of the salt as well as temperature, definitely, because temperature also acts against that formation of, because temperature acts like increasing the entropy, right? So finally there is a balance somewhere. If you compare different ions, for example, monovalent electrolytes or divalent electrolyte, so you can calculate, in fact, this Debye screening length. And finally, if you plot Debye screening length, the surface separation. So, for example, if you take 2 colloidal particles with a radius of 1 micron and with surface charge density of 2 millicoulomb per meter square, and they are suspended in electrolyte, which is monovalent. Okay, and if you this y-axis is basically double layer force in piconewton, which can be easily calculated in using modern day AFMs. And this is surface separation. You can see the double layer for high concentration for 30. These are all monovalent, not divalent or trivalent. If you see that if the concentration is very high, the double layer, the screening length is shortest. So because the charge density is so high, you have more number of counter ions. So the screening is very dense actually, and then it falls very rapidly. So if you have less dense counter ions, 1 millimolar, then okay, it will take its own time, and then this double layer will be quite widespread, and it will fall off slowly actually. So this is so you have tremendous application. I have not put the applications of that, but you can see in the electrochemical cells, they're all around these supercapacitors. There's so many applications coming up of these basic electrochemistry, which has come out of DLVO theory. And if you put another surface, for example, in a electrochemical cell, so close to each other, and also we can have lot many examples in nature. For example, these straws, where in plants, where this plant fluid or whatever flows, and inside the plant sap, they're all these electrolytes actually, right? All salty electrolytes. So there also the science works. I don't have example in detail, but I am also interested to give. Here I'll put more examples next time. It's very interesting actually. I'll connect it to the nature, this one. I don't have an example right now. Okay, so but how to understand in a systematic manner? So you should give a lot of regards and respects to these four scientists actually. Number one is Boris Deryagin, and he was born in 1902 and died around 1994. And he is one of the founding person. He laid the foundation of actually what we call it colloids and surfaces. You know that there are a lot of journals on colloidal chemistry. Langmuir is actually one of the most famous journal for colloids is Langmuir. And then there is a journal of colloidal surfaces, colloidal chemistry. So many journals are there in chemistry. So you can go back to 120 years when this guy was born, and probably he was thinking about these things 90 years back when he was a young guy like you about colloids. So he laid the foundation of this. And where I sit, actually, a lot of work, historical work on colloids was done in NCL when NCL was founded actually late 50s and early 60s. Okay. The second name is Lev Landau, and all the physicists, they know him. He was one of the brightest brain, one of the brightest actually, Lev Landau. He's mathematician and physicist together, actually theoretical physicist. He got Nobel Prize in '62 for his development of. You can see that a chemist coming into the play, colloidal chemist. I mean, there was no chemistry at that time. It was all alchemy. Alchemy slowly became chemistry. Same thing with physics also. But physics became physics from astrology to physics transition became much earlier. That is the only difference. But we all started the same journey. So he is credited to invent superfluidity, and he got the Nobel Prize for that. Right. So now this is interesting to make you laugh. I keep some humor at hand. So this is just out of syllabus, but it will make you smile and laugh, and you can share with your friends. And see, Landau used to keep with him a piece of paper, which is now it is called Landau's list actually. Okay, and he used to keep the name of all the physicists which he ranked on logarithmic scale of productivity, ranging from 0 to 5. Okay, highest was 0.5, and he assigned in his list that rank Of course, to Albert Einstein, according to him, Albert Einstein was highly productive. It is a productivity list, okay, logarithmic scale, okay. So logarithmic scale means 0.1 to 0.5 to 1 is a big jump, and 1 to 2 is a big jump. Okay, there is a big gap. It's order of magnitude difference from 1 to 2. And rank 1 was awarded to historical giants like Newton and Wigner, and quantum mechanic giant like Niels Bohr, Heisenberg, Dirac, Schrodinger. So they gave into rank 1, and he ranked himself on that scale at 2.5, and he later promoted himself actually to a scale of 2. And how he could do it, it basically puts a smile. So so you can also draw this scale and okay, and rate all your friends. That's sort of fun. And this is a picture of Niels Bohr and Lev Landau in Moscow, two giants in 1961. And third name is again close to my heart actually, and I should pay a lot of gratitude because my own career was proving his theory, in nanoscale size. Basically, I won't go into that in detail, but he published one paper on iron oxide, and it's called Verbe transition in iron oxide, Fe3O4, which later in 2002, I published one historical paper where I proved that Verbe transition does exist down to 10 nanometer, because there was a lot of controversy whether my students are aware of that article, some of them. So he was a hardcore theoretical physicist. He worked in the Phillips research laboratories and hardcore physicist actually. But he worked a lot on physical and organic chemistry, which nowadays physicists they didn't want to work. I was telling an example of one of my students. Anyway, I'll not discuss because it's called getting recorded. So he worked a lot on stability of lyophobic colloids, and he worked a lot on this double layer. This is his paper in I think Journal of Physical Chemistry, 1947. This bifurcation in A, B, C, Journal of Physical Chemistry A, B, C happened I think around 2006 or something, when I published my own first paper from NCL with Ramya Jagannathan. So then that time I think it happened. So theory of stability of lyophobic colloids, and he published from physics Phillips laboratories in Holland, Eindhoven actually. And I was supposed to be, I got a postdoc in spintronics long back. I didn't join in Eindhoven Institute of Technology. Anyway, so fourth aim is over B, and he again worked on this theory to complete it as a DLVO theory. Okay, Derjaguin, Landau, Verbe, and Overby. These four giants contributed to one single formula, which we call to explain this colloidal stability. When you make nanoparticles, the question is that why are they stable? Of course, we know this Brownian motion, steric repulsion, and of course, this charge-charge interaction is there, which can be understood by this interaction between electrolyte as well as these colloidal particles. So you can see that this van der Waals attraction and the balance between van der Waals attraction and double layer repulsion, finally you reach to some similar kind of curve. So we can have a simple equation. We need to just add up. This is the force, electrostatic force, as a function of Z. Z is the distance. Again, we are taking two spheres. Okay, here we are taking one sphere, another is a planar surface. We are taking this example from this book. Okay, so this part is electrostatic force, where your R is basically the sphere of the radius, and okay, so, and this is a Hamaker formula. H A is the Hamaker constant, R is the radius again, and Z is the distance. So finally it is, and you can see this is exponentially falling. and lambda d is Debye screening length, which we already know. So you can now you can see that how this at particular distance both the forces can balance off and probably become zero. Somewhere here they become uh, zero. But if one of the forces is stronger than other, you can have net repulsive or attractive forces. Uh, or if you eliminate one force, if you eliminate this force, like in Sundarban delta, you can have only attractive force left and strong van der Waals interaction. So with this, I close today's lecture, and let us open this up for